decimal fractions in other number bases. Normally, when we have it in general system or our number or decimal, our number 10, if you have something like this, 0.142, you know this one is going to be tenths. 0. So we are going to have 1/10, 400, and 2,000. So, which implies 1/10 plus 4/100 plus 2/1000. You understand? So if we have something like this in base 5, let's say 0.142 in base 5, what it implies is this: 1/10 base 5, 1/400 in base 5, and 2,000 in base 5. So this will now be 1/5 plus 4/5 squared. Remember, this is 10 squared plus 2/5 cubed. So if I am to convert this one to base 10, this is the operation that I will carry out. You can see, if I am to do this and convert it to base 10, this is the operation that I will carry out. So which means that if I want to now convert something like this in base 10 to this place, I will have to, you understand, instead of my division now, there will be continuous multiplication. Just like before, there will be multiplication. Do you understand? So now we have understood how to convert decimal fractions from one base to base 10. From one base to base 10. So this one, that is how it is. So by the time I do every other whatever using my calculator, I will get the fraction value of this. Now let's see how I convert from base 10 to other bases. Now I have to convert 0.526 base 10 to base 8. You know, when it is whole number and we are converting from base 10 to base 8, we have to do continuous division by 8 and writing out the remainder. But now, when we are converting from base 10 to base 8, we are going to do continuous multiplication. And we will now write out the whole numbers. That's what I mean. I have 0.526. I don't want to put this in. So, this is going to give me 4.208. The next step is I will multiply this fraction side by 8 again. So I'm going to have 1.664. I'm going to multiply this by 8 again. So I'm going to have 5, 3, 1. I will continue until I am satisfied. Let me do it one more time. So this is going to give me 2.496. So, you know, in the other instance, we wrote upward. But in this instance, we write it downward. So this is going to be 0.52610 is equal to 0.41528. So you can see the way out. All of these processes, they are now clear to us. If we are going to use okay, let me just leave it there. Now let's quickly work on this. It says that we convert 384.426 base 10 to base 12. You know, like I told you, you can have it in any number basis. We are still going to do some special number basis. The normal way you convert from base 10 to any other number base, that's the one way you will do it for base 12, base 13, base 16, base whatever. And because 10 is the one we are used to, that's why it's like this. Now let's see what we are going to do. You know, this is combination of two patterns. One whole number, the other fraction. So this is going to be 28, I have 3. Remaining 2. 12 is 24. 2. So remaining 0. 12 now again. 12 is 32. I have 2. Remaining 8. 12 is 2. 0. So this portion is going to give me 2, 8, 0 is 12. You can see how I did that. This one, I have done this one. Now, I will have to work on this portion. So here we have 0.426. Like I said, I don't want to put anything here so that I won't have any error. Multiply by 12. So I'm going to have 5 here, 0.112. Again, I multiply this by 12. That gives me 1.344. Multiply again by 12. So this gives me 4.128. Let's multiply one more time. So this gives me 1,536. So I have to copy it downward, and that's going to give me 0.5141. So it's going to be 280.5141. I might add that one, I might remove it. So you can see how easy it is. It is just for you to know where it is fraction, what do I do? Where it is whole number, what do I do? This is about conversion from, what's it called? Base 10 to any other number base. You can see when we are converting to any other number base from base 10, we are dividing. We are dividing if it is whole. But if it is decimal, we are multiplying like this. So that one is done. Now, we are converting from another base to base 10. And you can see that this one has fraction. That's the difference between this one and the other one we have done. So what do we do? 357.321 base 8 to base 10. Like I said, we have done the fraction part before and the whole number part. So let's merge the two together. That's the difference between this one and the other one we've done. We have merged here. So here, the normal thing is to multiply. And we are going to do it 357.321 base 8 to base 10. So we are going to multiply by different numbers, powers of 8. So we have 3 times 8 plus 5 times 8 plus 7 times 8 plus 3 times 8 plus 2 times 8 plus 1 times 8. Please take notes. The power ends here. The points start from here. So you are going to make it from 0, 1, 2. Here, you are going to make it minus 1, minus 2, minus 3. Another way you can write it is this. 3 times 8 plus 5 times 8 plus 7 times 8. So, you now make it like this. 3 divided by 8 plus 2 divided by 8 plus 1 divided by 8. So you can see now. So we are going to have 0 here, 1, 2. We are going to have 1, 2, and 3. So, with this arrangement, you can easily do your work straightforward. Once, by using the calculator. So, let's see. So, the answer is going to be. So, you can see. On using calculator direct, get me an answer. Straight. So, that's the way to do it from one base to the other. From base 10 to other bases, and from other bases to base 10. Now, let's talk about some number bases that are of interest, special. I would like to talk mainly about binary, binary, octal, decimal, and hexadecimal. Generally, we have talked about it before. That one has number ranging from 0 to 9 that we can combine. This is the everyday number we use. So we can always have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. These are the digits that you can find under the binary number base. These are the digits you can find, and we know how to perform our operations under this one. this denary, and any other thing we can do, multiplication, and how it is being represented. That's all about denary, nothing special about it. The next one is binary. So when they say binary, it means two. The numbers you can find under binary system, the figures are 0 and 1. 0 and 1. And these are numbers these are the figures you can find under binary. That's the special thing you can see about it. The other one we have to talk about is octal. This octal means base 8. And we all know that 8 is equal to 2 cubed. So we talk about the relationship between base 2 and base 8 later on. Octal. The numbers you can find under octal are 0, 1, 2, 3, 4, 5, 6, and 7. So we have done about the conversion from one form to the other. So this is the thing we can say now that is special under octal. Now go decimal. When we are talking about decimal, we are talking about base 12. And you know, when we are talking about the 10th of any number base, it is the base. So under this base, 12. You understand? Will be equal to 10 in base 12. 12 in base 10 is equal to 10 under base 12. So look at the way the numbers are. We are going to have these figures. These are the figures you can see or find under the decimal. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Instead of 10, we have x here. You can see. And then we have this. You can see. So the 12 now will be 10. I hope you understand now. So that is what we have under duodecimal. We have talked about the conversion and all this stuff. So here, I can talk about it. I have 2x 5 goes like this, 0.89x is 12. You understand? This is 10. This is 11. But they can stand alone, like a figure under base 12. And this 10 is the 12 under base 10. So you can see the interest here now. Let's talk about the last one. Now let's talk about hexadecimal. In this place, we are talking about base 16. And like I did when I was explaining octal, take note that 16 is equal to 2 to the power 4. We are still coming to the use of this. And the digits you can find under hexadecimal are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 8, B, C, D, E, F. So here, A is 10, B is 11, C is 12, D is 13, E is 14, F is 15. So you can see how it is being represented. Every other operation, every other conversion can be easily done here as the other ones you have done, either from base 10 to base 16 or from base 16 to base 10. Anyhow, you can easily do that. So if you are converting like let's say 9a base 16 to base 10, you know what it will be? It's going to be 9 times 16 plus a times 16. So we put 0, put 1 here. And that will be, I think this is 144 plus, what is this one? 10. So this is 154 is 10. And this is 9a is 16. So you can see straight. So you don't compare it as separate number. Consider it as whole number. That's it. Now, let's talk about the use of octals as intermediates. This is just an example to practicalize it. But I want to show you the step. Okay, the easiest way is to use an example like this. When we have a number like this in base 10, I want to convert to octal, binary, and hexadecimal form. You know, reasoning will be like, okay, Let me convert from base 10 to octal, base 10 to binary, base 10 to hexadecimal form. But it's not necessary. Once you get it to octal, it makes your job very easy. Or even if you make it to binary, you can easily convert from binary to octal to hexadecimal form. Very easy. You understand? So, between these two, you can easily work every other way out. Please, I am restricting it to octal, binary, and hexadecimal. Take note. Now, let's do it. Let's use our octal as intermediary now, not binary. I like using octal because it will be shorter. But by the time you are using binary, you know, base 2, your division will be longer. Now, let's see. If I want to convert this one to octal, I will divide first by 8 and write down the remainder. So I have 3. So, it will be equal to 348 base 10 plus 0.654 base 10. So I convert this one to base 8 and I convert this one to base 8 separately. Let's see that. I have 348. 8 here. 4. In 28. 3. I have 4. 8 here is 5. 3. 8 here. 0, 5. So this one I write it off. So this will be equal to 5, 3, 4, 8. Now let's work on this. You know how to do it now. And now, for this part, let's do it now. 6, 5, 4. We multiply by 8. So this. So I'm going to have 5. 0.232. I multiply this point again by 8. So I'm going to have 1.856. I multiply again by 8. This gives me 6.848. I think I have done this one before. So this is giving me 6.784. So this portion will now be, I will now write it down. So this will be 0.5166 base 8. So everything will be 534.516. Let me make it 517. So we have done this, we have converted it to octal. Now, from this point, we convert to binary. And from binary, we convert to hexadecimal. You know, I told you something the other time. I said 8 will be equal to 2. So which means that 8 in base 2 will be equal to 1000. 8, yeah, 8 will be equal to 1000 base 2. That is it. That is 10 times 10 times 10. Now, what do we do? What are these numbers in base 2? They will be in 3. Are you getting me? They will be in 3s. So we will now express it one after the other. And later on, we match. Let's see what this will be. 5, 3, 4, 5, 1, 7. What is 5 in base 2? That is 101. 3 in base 2, 11. 4 in base 2, 100. 5, 101. 1, 1. 7, 1, 1, 1. But you must express everything in 3s. In 3s. So this one will be 0, 1, 0, 0, 1. Since I have done this, to now convert this one to binary, you see what I do. So I will now be writing their equivalent in base 2. I will now be copying them out one after the other. So this one will now be equal to 534.517. This 8 will now be equal to 1013. Mind you, please note, I added 0 in front to make it 3. 0, 1, 1, 400, and 4. That is 100 points. This is 101. 101, 001, 111. You can see. So if I am trying to convert straight from base 10 to base 2. You can see how long it will be. So if I convert it first to base 8, and from base 8, I convert to base 2. You can see how easy it has made my job. Now, the next thing, from base 2 now, I convert to base 16. Now, you see, I now mark this one in 4s, as in 4 digits, to make it, to convert it to base 16. Let me show you what I mean. You know, I told you, 2 raised to the power 4 is equal to 16. Therefore, 16 is equal to 10,000. So, you can see this is 5 digits. So, I try to form the digits into 4, 4. And from there, I will make it into what I want in base 16. Just like I have done here, you know. Which means that I can easily convert from this base to base 8. And from this base to base 16. Just like I have converted from here to base 2. Let's see. You know, I have 101, 001. So I have to make it into 4, 4. 0011. That is 1, 4. 0, 1, 0, 1, 0. That's another one. And from here, I have to add 3 zeros. Please take notes. I have to add 3 zeros. The next one now, from here, I have to make it 10, 10. 0, 1, 1, 1. And from here, to make it complete, 0, 0, 0. You can see. If I add the 0 here, it doesn't change the value. Because the 0 I add here is not changing anything. So from this place, I will now look at what this one is under 2, under base 2, equivalent in base 10. And that's what I will write down. Just like we did by converting from base 8 to base 2. Let's see. 0, 0, 0, 1. 0, 1, 0, 1. One, 1, 0, 0. Here again we have 1, 0, 1, 0. 0, 1, 1, 1. And 1000. So what does this one give us? Here this one is 1. At least I know that one. Here this one is 8. This one is 5. 0, 1, 0, 1. This one is 7 here. This one is 1010. This one is 10. Because 1000 is 8 plus 2. That's 10. This one is 1100. That is 8 plus 4. So this is 12. So, and that will be 1, 5, 12, 10, 7, 8. So, I'm now going to write it out as I ought to write it. It's going to be 1, 5, 12 under base 16. 10 is A, 11 is B, 12 is C. Points. This one is A now. 7, 8. So you can see how fun and exciting it is. Instead of converting from this place to octal, from this place to binary, from this place to hexadecimal, you can see how easy we have done the whole thing. At the same time, if you have it in binary, you can convert from here to here, from here to here. You can even convert from this place to this place. You can see now, you can convert from this place to this place now. So it's easy. Now let's consider the reverse operation. We have to express 4b2.1a6, 16 in equivalent binary, octal and binary. So what do we do? We have 4b2.1a6. Let's convert it first to binary. Just like we did the other one. We have to express each of them in 4 digits of binary. So we are going to have 4b2.1a6. This one is 0, 1, 0, 0. Yeah. This one is 0, 0, 1, 0. 0, 0, 0, 1. I think 6 will be 1, 1. 1, 1, 0. Yeah. And here B is 11. And that is 8 plus 086 will be 0, 1, 0, 0, 1, 0, 1, 1, 0, 0, 1, 0, point. Okay, let me write it down here for space. Because of space. Is equal to 0, 1, 0, 0, 1, 0, 1, 1, 0, 0, 1, 0, point 0, 0, 1, 1, 0, 1, 0, 0, 1, 1, 0. So you can see, it can be easily converted to base 2. And from base 2, you can easily convert it to base 8. And from base 8 now, you can convert that one straight to base 10. Very easy. Now let's see how we convert this one to base 8. We will arrange it in threes, just like we did the other time. So this one is now going to be 1 here, 2 here. So this is, I have 1, 2, 3. So in this case 2, 3, 3. Now from here, 0, 1, 0, that is 2. 0, 1, 0, that is 2 again. 1, 1, 0, that is 6. 0, 1, 0. Yeah, 0, 0, 0, that is 0. 1, 1, 0, that is 6. 1, 0, 0, that is 4. 1, 1, 0, that is 6. And that is base 8. 2 to 6 to 0, 6, 4, 6. That is base 8. Now, let's now convert from base 8 to base 10, which is very easy. This one will now be converted to, convert this to base 10. So it will now be equal to 2 times 8 plus 2 times 8 plus 6 times 8 plus 2 times 8. So let's do it like this. 0, 1, 2, 3. For this portion, I'm going to have 0 times 8 raised to power minus 1 plus 6 times 8 raised to power minus 2 plus 4 times 8 raised to power minus 3 plus 6 times 8 raised to power minus 4. Now that's what the calculator will give us. So the answer is 1202.103. So you can see, it's just like playing game from one point to the other.